Welcome back to The Explainer. Today, we're looking at something that honestly might just change how we think about science class forever. For a really long time, we've relied on flat, static textbook pages to try and understand these incredibly dynamic, three-dimensional physical realities. But today, we are exploring the absolutely critical leap from passive reading to interactive discovery, literally bringing science to life through digital simulations.
It all starts with a fundamental question. How do we safely turn student curiosity into action? To really grasp complex science, students need to get their hands dirty, right? Metaphorically speaking, of course. But doing that in a physical space comes with some pretty heavy baggage, like the very real anxiety of dropping a wildly expensive glass beaker, or, dealing with the lingering smell of sulfur in the hallway for a week.
Okay, so let's dive right into this. Here is our roadmap for today. Number 1, the limits of traditional labs. 2, enter the digital simulation. 3, 7 benefits for students. 4, the science of interactivity. And finally, 5, building STEM confidence safely.
All right, let's jump to section 1, the limits of traditional labs.
So, traditional physical labs are foundational, sure, but let's be real. They come with some severe friction points. They can be hazardous with chemical spills, they are incredibly expensive to maintain, and often, because materials are just so scarce, experiments end up being a one-time event. But contrast that with the modern virtual lab. It's completely safe, massively cost-effective, and inherently repeatable. You are literally no longer bound by whatever happens to be left in the physical inventory closet.
Moving on to section 2, enter the digital simulation.
Let's clearly define what we're actually dealing with here. A digital simulation is an immersive, interactive, computer-based tool. But the real magic? It's the experiential learning. You see, this isn't just sitting back and watching a video of an experiment. It's actively manipulating variables yourself and getting immediate feedback in a totally risk-free environment. It takes these huge, abstract ideas and suddenly makes them tangible. And the beauty of all this is that it doesn't abandon the scientific method at all. It completely embraces it. Students still perform the experiments. They still collect the data, analyze the results, and draw their own conclusions. They follow the exact, rigorous scientific process required to truly learn, just without ever needing to handle a hazardous chemical or share one single expensive microscope with 5 other people. Which brings us to section 3, 7 benefits for students. Now, what's really interesting about this is how it creates a comprehensive educational ecosystem. We are bridging the gap between molecular chemistry and high-level theoretical physics, all under one unified digital roof. Here is the quick bird's-eye view of those 7 core benefits: safe environment, enhanced understanding, increased engagement, accessible anywhere, cost-effective, repeatable, and personalized learning. But to really grasp the impact here, we need to see how these actually multiply each other's effectiveness when they're paired up. For instance, think about combining safety with cost-effectiveness. By removing the physical hazards, the spills, the broken glass, the toxic fumes, you instantly remove the financial burden of constantly replacing those materials. It's the ultimate safe sandbox for students, and it doubles as a massive logistical and budgetary win for schools. Then there's the incredibly powerful combination of accessibility and repeatability. In a physical lab, when the bell rings, the experiment is over, done. But digitally, a student can learn from any device, anywhere. And if they don't quite get the concept the first time around, they can try an experiment a dozen times until it clicks. It completely shatters time and location barriers. And when we pair enhanced understanding with personalized learning, something really special happens. When you take a complex abstract theory and make it tangible right there on a screen, you naturally cater to individual student needs. Students are completely empowered to learn at their own pace, tweaking scenarios until that exact light bulb moment happens for them personally. Okay, section 4, the science of interactivity. So we know it's safe and cheap, but does it actually improve learning? Let's take a look. It's honestly incredibly exciting to see the research validate the theory here. So the crucial point is that when interactive molecular model simulations are used during chemistry instruction, there is a significant, highly measurable boost in students' understanding and academic performance. This is especially true with notoriously tricky concepts like chemical bonding. The data absolutely backs up the integration. And the reason this works so well is because we are moving far, far away from passive learning. Passive learning often just looks like trying to memorize formulas written on a whiteboard. But active engagement, that involves dragging elements around, testing bold hypotheses, and getting instant feedback. It keeps the brain actively firing, and crucially, it turns the student from a mere spectator into an active participant.
Let's move to Section 5 and see how this works in practice. Building STEM confidence safely. The source material actually highlights platforms like PraxiLabs as a prime example of this shift. This isn't just a basic 2D flash game. No, it is a 3D, fully immersive virtual simulation explicitly designed to closely mirror the exact equipment and procedures of a real-world physical lab.
And this brilliantly illustrates how these digital environments successfully unify the three core science branches: biology, chemistry, and physics. It provides a highly comprehensive approach to STEM, bringing all of these historically separate, incredibly resource-heavy disciplines into one single, accessible digital space.
Inside these simulations, students aren't just, clicking next to read a new paragraph. They can instantly modify precise variables. They can tweak the force, adjust the speed, alter the voltage, or change the resistance. And then they observe how those specific physical changes instantly affect the outcome. It deeply encourages genuine, trial-and-error scientific inquiry.
Ultimately, platforms like PraxiLabs are turning science into a truly hands-on digital experience. We remove the physical hazards, we remove the harsh resource limits, and by allowing that unlimited repetition, we are literally raising the overall educational standard.
Digital simulations create a confident, flexible, and inquiry-driven experience that, and I love this quote, transforms curiosity into meaningful understanding. It perfectly bridges that critical gap between wondering what if and actually discovering what is. So, I want to leave you with this provocative final thought to consider for your own educational spaces. How will your institution adopt this technology to safely turn student curiosity into action? The tools to bring science to life are right here, they are safe, and they are infinitely repeatable. It's time to start experimenting. Thanks for joining me on this explainer, and keep learning.